Hello, this is Erik from UNC Charlotte. This is joint work with Maruf Hossain, who just defended his PhD. We present contributions to high-performance temporal graph analysis. Most HPC work in graph analysis is in one of two settings. In the first one, we have a graph and we are trying to compute some expensive analysis, like centrality or clustering. The graph is usually large and static, and the problem is to process it as fast as possible. In the second setting, the graph is being streamed to the system, with vertices and edges being added as time passes. The challenge is to maintain an analysis like centrality or clustering when the graph changes. The performance issue is to enable supporting the highest rate of change in the graph while maintaining the analysis up to date in real time. By comparison, postmortem graph analysis is the problem faced by an analyst receiving a graph that was constructed over time and trying to understand its structure. Vertices and edges have time information embedded on them, and we want to compute the result of a particular analysis at different points in time. The postmortem setting can be thought of as an offline setting for temporal analysis. Postmortem analysis does not receive much attention despite being highly useful and computationally expensive. It is a problem that is different than both the static setting and the streaming setting. Postmortem analysis can leverage the techniques of the classic settings, but also present additional opportunities for performance improvement. In this presentation, we look at a particular postmortem analysis, the calculation of PageRank on a sliding window graph. We show that postmortem analysis can be much faster than using static and streaming techniques by leveraging a combination of graph representation, incremental algorithms, parallelism, and data reutilization. In this paper, we assume that the temporal graph is defined by events that happen at a particular point in time. An event induces a temporal edge that will stay in the graph for a fixed amount of time, known as the window size. We refer to the graph at a particular time as a window graph. The event could be two scientists co-authoring a paper, or two individuals visiting the same establishment at the same time. The edge doesn't stay in the graph unless the interaction is being repeated over time. We will perform the analysis at regular intervals, known as the sliding offset. The analysis we perform is the classic PageRank. It identifies important vertices by converging a random software model on the graph. A probability distribution on the vertices of the graph is iteratively distributed throughout the graph until convergence. In the postmortem temporal setting, we want to compute the PageRank of every vertices in the graph for every window graph in the dataset. In postmortem analysis, the entire temporal graph is known in advance. This is advantageous compared to the streaming and static model, since a representation of the graph can be computed once and for all for the entire analysis. Here, we can represent the entire graph in a temporal CSR format, where each edge is associated with the time of the event that induces that edge. It enables to enumerate the edges of a particular window graph by enumerating the temporal CSR format once. We will present results on the Wikitalk graph, but you can see other graphs in the paper. We compare performance to a simple static implementation that builds every window graph from an edge list and compute PageRank with the vertex parallel algorithm. We will also compare to a streaming PageRank implementation of Stinger. Overall, a basic postmortem analysis is faster than a streaming or static baseline, because postmortem analysis saves time in data management of the graph. But we can go further. We can use incremental techniques developed for PageRank. The PageRank of a window graph is not that different than the PageRank of the next window graph. Overall, we can reuse the PageRank values from one window graph to the next by proportionally distributing them to the vertices that remain between the two window graphs. The performance improvement obtained by this partial initialization is significant, and it is larger when there are more common edges between the two consecutive window graphs. A disadvantage of the temporal CSR representation is that listing the edges of a window graph requires listing every temporal edge in the dataset. You could have a situation with only 10 edges in a window graph, but 1,000,000 temporal edges needs to be considered. A solution is to split the temporal CSR representation in multiple chunks, we call multi-window graphs. By controlling the number of multi-window graphs, we can control the traversal overhead. Of course, there are temporal edges that will need to be replicated in 2 multi-window graphs, which will cause a storage overhead that needs to be managed. There are 2 natural levels of parallelism in the application. One can process different window graphs at the same time. One could also leverage parallelism inside the kernel of the analysis, on PageRank by performing vertex-level parallelism for a particular window graph. We leverage both levels simultaneously and use a nested form of parallelism. One needs to pay attention to load balance in such a situation, since 100 vertices worth of computation in the first window graph can represent a vastly different amount of computation as 100 vertices in the last one. Processing simultaneously 2 consecutive window graphs prevents partial initialization, which is a significant runtime improvement. For these reasons, we use a work-stealing engine to manage our parallelism. At first, threads will be allocated a chunk of contiguous works. It enables partial initialization for most of the window graphs. And eventually, contiguous blocks of work will be broken down to ensure load balance. Looking at performance results highlights that nested parallelism performs better in almost all situations. Also, using a larger number of multi-window is usually preferable as long as the memory overheads are kept in check. We can also reduce the amount of data transfers. The key realization is that k window graphs within the same multi-window graph have the same representation in memory. Therefore, one can traverse the k window graphs at the same time. This is similar to a classic optimization in linear algebra, where instead of performing k matrix vector multiplications, one can perform one matrix-matrix multiplication where the second matrix is composed of k columns. It saves memory transfers, and it benefits from more regular access pattern in sparse cases. For postmortem PageRank, we need to be careful which PageRanks get computed simultaneously. We do not want to process window graph 0, 1, and 2 simultaneously, because that would prevent partial initialization. Instead, we will perform window graphs 0, 10, and 20, and then we will perform 1, 11, and 21, because they will benefit from partial initialization. The performance results show that this optimization is preferable in all non-degenerated cases. Studying the performance by varying the size of the window and the sliding offset shows that the postmortem techniques can be hundreds of times faster than streaming analysis. We showed in this paper that a postmortem analysis of PageRank is a performance problem that is deeper than static analysis and streaming analysis. By carefully leveraging algorithms, graph representation techniques, parallelism, and data reuse, we were able to perform temporal PageRank analysis hundreds of times faster than an optimized parallel streaming strategy. While we considered the case of sliding window event model of temporal graphs, the techniques we presented do not strongly depend on that model, and they extend to any temporal graphs. We believe that data analysts can benefit from high-performance temporal graph analysis tool, and we look forward to extend our methods to analyses more complicated than PageRank.